Dear students, in this class, let us discuss the most important concept of transistors, that is transistor biasing. In the last classes, already we have seen the fundamentals of the transistors and concluded that out of the three configurations of the transistors, common base, common emitter and common collector, the common emitter configuration is much more popular. And taking this common emitter configuration as the basis, let me discuss the concept of the transistor biasing. So, in this lecture, we are going to see the reasons for the popularity of the common emitter configuration and why biasing is required for the transistors and what do you mean by the operating point and load line. So, for this one, let me take this common emitter configuration. So, this is an NPN transistor and here emitter is common for both input and output. So, emitter is grounded here, that is why it is a common emitter configuration. In the common emitter configuration, we are going to take the output at the collector. So, this is the output V0 and RC is nothing but the collector load resistance and RB is nothing but the base resistance. And you know very well, to act the transistor as an amplifier, to use the transistor as an amplifier, transistor must be in the active region. What do you mean by active region? Active region means base and emitter junction should be forward biased and collector junction should be reverse biased. As it is an NPN transistor, collector junction should be reverse biased means N should be given to positive because this is VCC is positive. So, you can extend like this is positive and this is negative. So, this is VCC. So, N is given to positive and here for the base junction P is given to positive here. So, that means emitter junction is forward biased, collector junction is reverse biased. That means the transistor is in which region? Active region. In the active region only we can use this transistor as an amplifier. And coming to these capacitors, and these capacitors, the property of the capacitor already told you in the rectifiers. The capacitor, the property is, if you take the reactance of the capacitor, XC is equal to 1 by 2 pi Fc. Of course, J is nothing but a phase angle, you can forget about. The magnitude is X is equal to 1 by 2 pi Fc. For DC, what is the frequency? Frequency is equal to 0 for DC value, DC signals. Then the reactance will be infinite. 1 by 0 is infinite. That means capacitor blocks DC. It doesn't allow DC. So, if you take this capacitor, it is named as CB, blocking capacitor. What do you mean by blocking? It is blocking the DC. Whatever the VBB you are giving to this transistor, this DC cannot be in this direction because this capacitor is going to block it. Exactly, if you are taking this output capacitor CC also blocks DC because this is the first stage of amplifier. And if the amplification is not sufficient, you have to add one more stage here, one more stage here, one more stage here. That is called cascading of the stages. So, whenever you are cascading these stages with other stages, only AC has to pass from this capacitor. DC should not be passed. So, that is the reason it is also blocking DC from one stage to other stage. So, as this capacitor is meant for coupling the signal from one stage to the other stage, it is called as a coupling capacitor. So, it is coupling capacitor and it is nothing but a blocking capacitor. But of course, the property is same. Everywhere the capacitor blocks DC and allows AC. Why it allows AC? If you are taking this AC here, F is equal to for AC 50 Hz. The frequency is equal to 50 Hz. So, if you take this 50 Hz here, the reactance will be having a value. Some low value of the reactance will be there. That means it offers low reactance for the AC and infinite reactance for the DC. That is the reason the property of the capacitor is it blocks DC and allows AC. So, if you are taking this transistor is particularly meant for amplification purpose. Amplification means if you are taking this here, this is the input signal Vs, and whatever the input signal you are giving is between the base and emitter. That means between the base and emitter you are giving the signal Vs, and you are taking at the collector. So whenever you are taking at the collector, the output will be maximum like this, same shape. Input is nothing but having the low magnitude here, but whereas output is having enormous magnitude, high magnitude. So whenever the signal is coming from input to output, the signal magnitude is much more. That means it is enhancing the signal strength. That is called amplification. So whenever it is doing this amplification here, the shape of the signal must be same. Here it is having a sine wave, it should be also having a sine wave. Then only I can say that it is faithful amplification. What do you mean by faithful amplification? If the output is the exactly replica of the input, then I can say faithful amplification is achieved by this transistor. Otherwise, suppose if you are taking the signal and passing the signal to the amplifier, and if it is coming in this way, like this, that means the shape is disturbed here. That means not the faithful amplification. Information is lost. So that's the reason. Remember always, the shape of the signal should be same. Of course, the magnitude will be different, because the amplification means very simple, my dear friends. You are enhancing the signal strength. For example, whatever I am speaking is a signal, and I am giving the signal to this mic here, and it is going to the amplifier. It is amplifying, and now so many students are actually listening to my lecture. If the amplification is not sufficient, very simple, you have to add one more stage here, one more stage here, one more stage here. That is cascading of the stages. Much more gain will be there. Generally, whenever you are going for the public addressing system, whenever you are enjoying this music and everything, you are getting so many types of boxes here, sound boxes. That means indirectly you are cascading the stages. And if the one stage is not sufficient for your music, you are going on adding the required stages, the entire public addressing system will be excellent. Exactly here, amplification is achieved whenever you are using a transistor in the common emitter configuration. So that's why, in order to get the faithful amplification from the input to the output, you have to bias the transistor. Biasing the transistor means you have to always put your transistor in the active region. What do you mean by the active region? Input junction should be forward biased, output junction should be reverse biased. Then only the signal can go from this to this without changing the shape of it. And that's the reason we are going for the biasing. What do you mean by biasing? Biasing means very simple. You are fixing the values of the collector current and output voltage. So there are two things you have to remember. One is the collector current, and other one is the output voltage VCE, because you are taking the voltage between the collector and emitter here. So this IC and VCE, actually they can be called as a operating point. Operating point means it is represented by the letter Q. Q is having the coordinates of both VCE and IC. This is nothing but the operating point. That means at what current and at what voltage the transistor is operating. That is called operating point. But here, if you are taking this circuit, you are using a common emitter configuration. Why common emitter? Common emitter configuration is much more popular. Already I told you. The common emitter configuration properties are actually matching the properties of an amplifier. So let me say very clearly, if you take an amplifier, this is an amplifier, let me say, this is a CA amplifier or CB amplifier or CC amplifier, it is an amplifier. So for an amplifier, always remember, you are giving input as well as output. This is nothing but the input and this is nothing but the output. Input is very low, output should be very high. That is nothing but the amplification. You are enhancing the signal strength like this. So for CE amplifier, the advantage is, if you are taking the current gain AI is medium. That means it is more. And if you are taking this voltage gain AV, it is also more. So if you are comparing the current gain and voltage gain with your CB and CC, it is maintaining the medium values. If you are taking the current gain is more for CC, but very less for CB. If you are taking the voltage gain, for CB it is very high, and your CC it is 1, it is an emitter follower. But if wherever you are taking the common emitter configuration, it is a compromising value between your CB and CC. That's why AI is medium, AV is medium. Automatically power gain AV is equal to AI into AV is also maximum. Power is more. And one more beautiful feature is, if you are taking the input resistance for this, it is very high. That is very, very important. And if you are taking the output resistance or not, it is very low, because you have to add a loudspeaker here. This is a loudspeaker. You have to match it like this. So, if you are taking the common emitter configuration, the advantages are current gain is more, voltage gain is more, automatically power gain is more. The input resistance is actually high. That's why it is maintaining isolation between the source and this network. And your output resistance is also very low. That's why it is very easy to match your loudspeakers here. That is the reason I can say, my dear friends, CE is popular. So many times he is asking why CE is popular. Very simple, you can say current gain, voltage gain, power gain, input resistance is very high. The only thing is output resistance is very low, which is very much required for the amplifier fundamentals. So whatever the properties I told you, all these properties are actually required for a good amplifier. Amplifier means which can enhance the signal strength. So you got the answer why C is popular. Why biasing? Biasing means very simple. If you do the biasing, then only there is a faithful amplification will be achieved. So whatever the signal you are giving, the same signal shape you have to preserve it. Then only you are going to get your signal strength here. Then only you are going to get your faithful amplification. Suppose if you are taking a song, and the song is input to an amplifier, and if you want to dance it, the same song has to come with loud voice. With loud voice means amplification should be achieved. But the same song has to come. Signal should not be disturbed. There should not be any type of distortion. Faithful amplification must be achieved there. So for getting the faithful amplification, we are going for the concept of biasing. Very simple, one more example I am telling you. For example, if you take a door, if the door is movable like this, it is moving upside or downside. If you want to just allow the total person into the room, you have to adjust the door upper limit as well as the lower limit. Suppose if you are actually maintaining, if you are not maintaining this, then if the upper limit is like this, my head will be cut. If the lower limit is upper side, legs will be cut. If you want to allow the total person through the door has to maintain the levels. The maintenance of those levels is nothing but the biasing. Exactly, in your transistors, if you want to just pass the signal from this to this without distortion, you have to see what are the values you are maintaining in the DC, VC and IC. And one more important point is here, friends. What is Q? Q means an operating point, quiescent point. You can say Q means here quiescent, Q-U-I-C-E-N-T, quiescent point. What is the meaning of quiescent? Quiescent means it is nothing but a zero signal point. Zero signal point is called as quiescent point. So, if you take this quiescent point, and which is also called as a zero signal point, then by seeing this value of the skew, whether the transistor is maintaining the proper biasing levels or not, we can understand. And one more thing is here, why it is called zero signal? If you are taking this diagram, here I am applying Vs, that means it is a signal. It is applying the signal. Then whatever you are getting here is also AC signal. Suppose if the signal is not applied, so for this circuit I am telling you, if the signal is not applied, then AC signal is not there. And here also you cannot get the AC signal here. And this AC signal will not be there. So only this circuit will be there. So now whatever the circuit that is remaining is only for DC. So before applying the signals, the transistor is biased in active region. Active region, that means emitter junction is forward bias, collector junction is reverse bias. To keep this transistor in this position, you are applying VBB here for forward biasing of the base, and you are applying VCC for reverse biasing of this collector. So this is forward biasing and this is called reverse biasing of the collector. So you are applying only DC volts and there is no signal at all. So whatever the conditions that are prevailing at this point, that means your VCE and IC are the DC values. Yeah, they are the DC values. I am calling it as an operating point, which is called as a zero signal point. Of course, in the later classes, for this circuit, we are going to apply AC and we have to see the amplification factor. But now I am concentrating only on the DC values. What are the DC values? You are getting VCE and IC. Now, what do you mean by operating point? Operating point is nothing but the coordinates of VC and IC. Now, I would like to demonstrate and what do you mean by this load line also. So, if you are taking the CE configuration out of the CB, out of the available configurations, CB, CE and CC, CE is much more popular, which is suitable for amplifiers. Now, let me concentrate on the CE output characteristics. So, what are the CE output characteristics here? Output characteristics means already I told you in the last classes, it is a graph plotting between output voltage versus output current. So, in the common emitter configuration, output voltage is VCE, output current is IC, but keeping input current as a constant. So, what is the input current? That input current is IB. So, this is IB1, let me say. So, you can say that IB2 and you can say that IB3 and IB4. So, like this, these are the characteristics IB1, IB2, IB3 and IB4. Okay. Now, these are nothing but the output characteristics of CE. Output characteristics of which configuration? CE. And if you take this CE amplifier once again and write the KVL for the output side. So, how to write the KVL? Your applied voltage is VCC, you are applying. So, VCC is equal to ICRC, this is IC, collector current into resistance ICRC plus VCE. So, applied voltage is VCE, the drop is ICRC and output is VCE. So, what is that equation? If you write the KVL for the slope and you can say your VCC is equal to ICRC plus VCE. This is nothing but the KVL for this output loop of the common emitter configuration. I would like to take this equation as the basis to demonstrate the concept of a load line. So, come to this figure now. So, these are nothing but the common emitter characteristics. In the common emitter characteristics, let me say, what is the basic equation just now we have written? VCC is equal to ICRC plus VCE. But my requirement is always output voltage VCE. So, what is VCE? VCE is equal to VCC minus ICRC. Now, this is actually VCE and this is nothing but the IC. And friends, on x-axis, this is the x-axis and this is y-axis. On x-axis, IC is equal to 0. So, I can say that here on x-axis, IC is equal to 0. Just substitute this in this one. If IC is equal to 0, VC is equal to VCC. VC is equal to VCC. So, therefore, VCE is equal to VCC. This is the first point I can say. So, on this VCC axis, let me say this is VCC. This is the value of VCC. VCC. On the y-axis, VC is equal to 0. So, I can say for the visibility, on y-axis, you can say that VC is equal to 0. So, if you substitute here, if VC is equal to 0, then VCC is equal to ICRC. Therefore, what is IC then? IC is equal to, I can say, VCC divided by RC. This is the point on y-axis. So your current IC is equal to VCC by RC. Let me say this is the point. So I can say that this is IC is equal to, this is IC axis. So let me say this point is nothing but IC is equal to VCC divided by RC. These are the 2 points. These are the 2 extremes. On x-axis it is VCC, on y-axis it is IC. Just combine these 2 points here and take a straight line which is combining these 2 points here. This is. So now if you are taking this one, whatever the line, just I am connecting this VCC by RC, and this is nothing but VCC. This is called as load line. This is a load line. Load line is nothing but the line joining the VCC by RC and VCC. But remember friends, we are considering only the DC values. We have not applied AC so far. So that's the reason I can say, strictly speaking, it is DC load line. DC load line. After applying the AC signal for my amplifier, whatever the line you are getting is AC load line. Now, this is a load line. These are the characteristics. And now, it is having so many intersections here. So, here it is intersecting, here it is meeting this, here intersection. Let me say this is Q1, and this is Q2, and this is Q3, and this is nothing but the Q4. So, the intersection of the load line with the characteristics of the commutator configuration, output characteristics, is called as operating point. So, operating point is nothing but the intersection of the load line with the characteristics. So, the operating point may be anywhere. This is Q1, Q2, Q3, Q4. Operating point may be anywhere. And we will discuss what may be the best location for the operating point. So, if you take any operating point here, this is the operating point. So, if you are extending like this is called as your VCE. And if you are operating this one, this is nothing but IC. So, operating point coordinates are VCE and IC. So, in future, if anybody asks you, calculate the operating point, means very simple, calculation of the collector current and VCE, means voltage between the collector and emitter. This way, you have to understand the operating point as well as load line. So, once you get this load line, and you are going to get this operating point. But the next one is, we are going to discuss it now, what may be the best location of the operating point, where we have to put it, whether Q4 is selected or Q1 is selected or Q3 is better, and we have to decide, because the location of the operating point should be at the center of the load line. Now I will prove it, why it is. So once you know this operating point, once you fix it here, then the operating point should be always stable. It should not disturb. It should not be disturbed under any circumstances, but the disturbance is taking place in transistor circuits, because your collector current is nothing but a function of temperature. If the temperature changes, automatically the location of operating point also changes. Now, let me say what may be the best location of the operating point. Okay. Now we are going to discuss what is the best location of the operating point Q. Just now I told you, operating point Q is nothing but the intersection of this load line with the output characteristics. It can intersect at any point of time. So, this is Q, this is also Q, this is also Q. But what is the best location of this operating point, and where you have to put it for the safety purpose? Now we are going to discuss it in detail. And remember, operating point is having the coordinates of VC and IC. It depends on IC, that means collector current. Collector current is also a function of temperature. If temperature changes, this location of the operating point also changes. We will discuss it later, but now let me tell you what may be the best location of this operating point. Now come to this figure. There are so many of your operating points. Let it be A, and this is B, and C, D, E, like this. There are so many operating points. Suppose if the transistor is operated at the point A, this is the operating point here. So what is the input for this? Input is nothing but the base current. So base current is nothing but the input current having the excursions like this. This is the sine wave, and the base current variation is like this. If the base current is given here like this, if the operating point is fixed at this point, that means near to the saturation region. I think you have remembered these CE characteristics. In CE characteristics, if you take IB is equal to 0 microamperes, the region below this IB is equal to 0, which is called as cutoff region. Cutoff region. The region left side of this line, this is saturation region. This is saturation region. Saturation. So this is the active region. In this active region only we have to utilize the services of a transistor as an amplifier. So let us fix the operating point Q at the point A. So this is the operating point Q. And the base variation is, the base current variation is like this. So if you take the output for this, output current IC is nothing but beta times IB. So this is the base current, and whenever you are extending the lines, you are not getting the exact shape of this input. And this positive cycle is clipped off. Why? Because the transistor is entering into the saturation region. If it is entering into the saturation region, positive peak will be clipped off. That means the distortion is coming into this picture. So what is an amplifier? Amplifier has to maintain the same shape, that is like input. That means we are expecting always a faithful amplification, but here faithful amplification is not there. So if this is the IC, and already you know VCE is equal to VCC minus ICRC. This is the basic equation for this. If IC is clipped off like this, automatically VC is also clipped off. VC means x-axis. So if you extend like this, and here also it is clipped off. So this is the portion of clipping. Faithful amplification is not achieved. The reason is the operating point is fixed towards the cutoff region. In the similar way, if you come for this figure, if the operating point is actually shifting towards the cutoff region, here B is the operating point now, and if you see the base variation here and here, this negative cycle will be clipped off. So whenever you are taking the output collector current here, positive is okay, the shape is, but the negative side it is clipped off. Why it is clipping? Because the operating point is set towards your cutoff region. This is the cutoff region. Cutoff region is the region which is below your IB is equal to 0, base current is equal to 0. So the lower portion will be clipped off. In the previous case, the positive portion is clipped off, and here it is the negative portion is clipped off. Distortion comes into the picture. There is no faithful amplification. That means you should not fix your operating point towards the cutoff region or towards the saturation region. So now let me say the conclusion for this operating point here. If you see this third figure, now I am setting the operating point at the center, that will be the C. See the point where I am using this operating point Q. I am setting the operating point Q. Q is a function of both VCE and IC. Now, if you operating point is at the center, and this is the base variation. So the variation of the base current is within the limits. And if you now draw this IC, the same thing you are going to get here. So if you are taking here, same thing you are going to get this. So if you observe here, as the operating point is at the center, shape is not disturbed, and you are getting the same shape as that of the base waveform. That means faithful amplification. So if the IC is like this, then automatically you can say that your VC is also like this. So this is the output voltage. So output voltage always depends on your output current. So in this case, what happens? Whenever the operating point is actually at the center of the load line, you are getting the full excursions of the signal. There is no disturbance in the signal. There is no distortion in the signal. There is no clipping at all. So faithful amplification is achieved. So finally, what is the conclusion now? Once you fix the operating point, better to fix the operating point at the center of the load line. So it may be the safest location of the operating point. Then whatever the input you are giving for the amplifier, same input with the amplified version you are going to get it, if the operating point is set at the center of the load line. So what is the best location of the operating point? the best location of the operating point is at the center of the load line. Okay. But once you set this operating point, always it may not be at that place. Operating point may always shift either towards the saturation region or cutoff region, because your Q is having the coordinates of VCE and IC. VC and IC. Your IC is a function of temperature. Your collector current is a function of a temperature. If temperature changes, your IC changes, and IC changes means your output voltage VC is equal to VCC minus ICRC. So if IC changes because of temperature, your VC also changes. That means the operating point changes. If the operating point changes, then there is a danger of getting a distortion into the system. So to avoid this, we are going to have different types of techniques. To fix the operating point, we are having some biasing techniques. Those biasing techniques are fixed bias, collector to base bias, and self bias. And to keep this operating point always at the stable position, you have to apply some compensation techniques also. Those things we are going to discuss in the next class. I hope you understood the most important concept of your transistor biasing, particularly why biasing is required, and what do you mean by this load line, and how to fix up this load line. And one more thing is, I can say that operating point. And one more point is here, I would like to tell you, if you take this is the load line, we are actually fixing this operating point here, and I would like to tell you what is the slope of this load line also from the basic equation. What is the basic equation? Basic equation VCE is equal to VCC minus ICRC. So from this I would like to write down the expression of ICRC. So ICRC is equal to VCC minus VCE. Therefore, your IC is equal to VCC by RC minus VCE by RC. VCE by RC. Therefore, this is equal to, your IC is equal to, IC is equal to minus 1 by RC into VCE plus VCC by RC. This is the expression you are going to get. Minus 1 by RC into VCE plus VCC by RC. So this can be compared with Y is equal to mx plus c. This is the basic equation of the straight line, where m is nothing but the slope and c is nothing but the y-intercept. Here what is the y-intercept? C, VCC by RC. That's why I told you this intercept is nothing but VCC by RC. Already explained to you in the another way. And what about this is VCC. This is VCC. And this is mx plus c. M means it is nothing but the slope. What is the slope of the line? The slope is nothing but minus 1 by RC. So whatever the line you are having, this load line having a slope with this slope is nothing but minus 1 by RC, which is nothing but m. M is nothing but the slope of the line. So it is another way of telling this load line concept. I hope you understood the concept of your load line and operating point and the necessity of the biasing. Once you know this, our duty is to keep the operating point always stable. So first of all, let me fix up the operating point for the transistors using some biasing techniques, and later we have to stabilize it by using your compensation techniques and other techniques. Okay, thank you.